Lecture 3 is entitled Rational Numbers. But before we can discuss what rational numbers are and some intriguing patterns involving rational numbers, we really need to look at the integers. And the key to understanding the integers is 0. For many years, you must understand, people thought there couldn't be a symbol that was something that stood for nothing. This was before television. In the 2nd century AD, the Greeks used the letter omicron, which is a letter similar to O. In fact, it's the short O in the Greek alphabet. And this was used because it was the first letter in the word Uden, which meant nothing. And it was a symbol to mean nothing, but people still had a hard time accepting that. The early Mayans used a 0 symbol as a placeholder in their base 20 system, but this was primarily used for calendars and times, and not for computational purposes. Probably the first use of a symbol for nothing, again as a placeholder, where we can trace that beginning to our current 0, was the use by the Hindus of a large dot called sunya. Sunya means empty, and it was used as a placeholder. Scholars still are unsure when sunya was first used. Opinions vary from the 3rd century AD to as late as the 12th century. Again, we had mentioned earlier in an earlier lecture that the Arab invasion of India picked up on much of the Hindu number system, and part of this was this representation of a symbol as a placeholder in a certain place. That is, if you wanted to write a number 302, you'd need something in the tens place. And the sunya was translated into Arab as sifir. And the sifir means vacant, empty, same as the sunya did. In the 13th century, when Europeans adopted the Hindu-Arabic system, the word sifir was Latinized to zephyrum. And this was used, and over a period of time, zephyrum became the word 0. I guess they got lazy and wanted fewer letters. And the large dot that originally was in India and was transposed over into Arabic countries became the 0 we know today. But it took a while. It took a number of years before that transition took its place. But in all cases, this vacant symbol was used as a placeholder. It was not used to represent nothing in the case of the answer is 0, as we would today. But as applications of mathematics got more complex, it became necessary to recognize that there was a quantity 0. And the set of numbers that start with 0 and continue with the counting numbers is called the whole numbers. And from the whole numbers, we can generate the integers. But we can't talk about that until we have the 0, this number that's less than 1, that really is nothing. And we have accepted, obviously, that there is a symbol that stands for nothing. The next thing we need to worry about now is the rest of the integers, which are the negative whole numbers. Now, what does this negative business mean? Well, there are real situations in the world where we have things that are in one of two directions. Examples: you can earn money and you can spend money. As an individual or as a company, you can make a profit or take a loss. Things can go up, things could go down. We could be traveling east, traveling west, traveling north or south. Some direction, be it a geographic direction like north or a direction like earning money, and its opposite. Gaining and losing, whether it's pounds or money or jars of peanut butter. You gain and you lose, opposite directions. A number on one side of 0 would be represented by a positive number, a positive direction, such as for profit, and the number the same distance on the other side of 0 would be the negative direction, and that would be, for example, a loss. Positive 2 is the opposite of negative 2. Now, if, for example, you decided that a loss was positive, then the gain or the profit would be negative. It's all relevant to what you decide is positive. Once you decide what's positive, its opposite is negative, and 0 separates the positive and the negative. Today, we have many uses. And for example, let's take a look at a situation if we had a small village and we had, on a particular day, 5 babies were born in that village, and unfortunately that same day 5 people died, what would the gain or loss in population be? Well, we'd have a positive 5 plus a negative 5. That is 5 gained, 5 lost, which of course would be 0. And we know that if 5 new people entered the population of that village and 5 people left the population, we would have no net change in population. Another common use for positive and negative numbers is the Dow Jones Index that's for the New York Stock Exchange. And when you watch the news reports, it will tell you that the Dow Jones is up 2.78 or down 23.46. And the up and down, in some cases, use arrows, in some cases, use a positive for up and a negative for down. In the National Hockey League, each player, other than the goalkeeper, is given a plus or minus number. Every time a player is on the ice, when his team scores, other than in a power play situation, I don't want to get involved in too much technicalities here, but when his team scores, you get a +1. And if you're on the ice when the other team scores, you get a -1. And you add it up. And a player with a large positive 15, means that when he was on the ice, his team scored 15 more goals than the other team scored. On the other hand, a player with negative 15 would mean that when he was on the ice, the other team scored more goals than his team did. And this is used partially to rank and rate players. Changes in test scores. Always reading the paper, our city or our county or our state test scores are up. SAT scores are up 2.37, or achievement scores, whatever it is. And they'll use plus if it's up, and unfortunately if it's down, they'll use a negative. Opposite directions. Integers, which are the positive and negative whole numbers in 0, have various rules for adding, subtracting, multiplying, and dividing. And sometimes it appears to many people that these rules came down from the mountaintop. Some person of importance went up and came down bearing a scroll and said, here are the rules for working with integers. Because it appears to be arbitrary, and it appears to be something you memorize and use and then maybe never use again. In actuality, the rules make a great deal of sense. We'll begin with the rules for addition by considering travel in a north-south highway. If I traveled 8 miles north and then traveled 10 more miles north, whether or not you understood integers, you would know that I'm 18 miles north of where I started from. That is, I traveled in the same direction, 2 different pieces, and the total was further in that direction. 8 north plus 10 north was 18 north. If I traveled 12 miles south and then went an additional 11 miles south, there's no question I would be 23 miles south of the point from where I started. When adding integers with the same sign, that is adding positives or adding 2 negatives, we keep the sign and add. So north plus north is more north, and positive plus a positive is more positive. So a positive 8 plus a positive 10 is positive 18, and a negative 12 plus a negative 11 is negative 23. But what if I traveled 12 miles south and then went 9 miles north? I would certainly not add. I wouldn't be 21 miles away from my starting point. In fact, I would be 3 miles south because I had gone 12 miles south and then turned around and went 9 miles north. Okay, what does this mean? Well, this means when adding 2 integers with opposite signs, you use the sign of the larger and subtract. So, for example, if I started out and went 13 miles south and then went 18 miles north, I would wind up 5 miles north of my starting point. Using the 2 examples I just gave as arithmetic problems, a negative 12 plus a positive 9 is negative 3. A negative 13 plus a positive 18 is positive 5. So to add 2 integers with opposite signs, again, we take the sign of the larger and we subtract the 2 numbers. To add more than 2 integers, really simple. Take all the positives, add them up. Take all the negatives, add them up. You will have 1 positive number and 1 negative number, and use that second rule to add those 2 numbers for your net answer. To understand subtraction of integers, one must first truly understand the meaning of subtraction. It's not necessarily taking away. The answer to a subtraction problem is called the difference. And the difference really is the missing addend, what I must add to the second number to be able to get the first number. 8 minus 3, we know, is 5. Since I must add 5 to 3 to get 8. If you can imagine 2 bars. one that was 8 high and a second bar to its right that was 3 high. And I said, what do I have to add to that second bar, the 3, to get to the 8? I have to add 5, and I'm going up, so the answer is 5. That's no problem. What happens if I do 8 minus 10? Now, we couldn't do this back in 2nd or 3rd grade because the answer then was there is no answer. But now we know about negative numbers. What must I add to 10 to get to 8? Well, obviously, I must add a negative because I'm getting a smaller number. And the answer is negative 2, since 10 plus negative 2 is 8. If I was using that bar diagram, I would go from 10 down 2 to get to 8. So therefore, again, the answer is negative 2. Another example is negative 2 minus 6. What do I have to add to 6 to get to negative 2? Well, obviously, I've got to add a negative quantity, and what I have to add is negative 8. So therefore, negative 2 minus 6 is negative 8. The question is, if you're trying to draw a diagram, one of those bar diagrams, how do you show a bar that's negative 2? Well, obviously, if the bar up is positive, a bar down is negative. And if you draw a negative 2 bar on the left and a positive 6 bar on the right, you will see to get from the second bar to the first bar, you must go down 8, negative 8. How about 6 minus a negative 3? What do I have to add to a negative 3 to get to 6? Well, obviously, I have to add something more than 6. It takes 3 just to get up to 0, and in fact, it takes a total of 9, because negative 3 plus 9 equals 6. Therefore, 6 minus a negative 3 is a positive 9. By looking at various examples using the missing addend definition of subtraction, it can be seen that one can subtract an integer by simply adding its opposite. That is, subtracting a negative 3 is the same as adding a positive 3. And subtracting a 6 is the same as adding a negative 6. Now, multiplication and division of integers can also be easily explained if we investigate simple patterns. The key is to comprehend what the meaning of multiplying by a negative is. Clearly, 3 times 4 means adding 3 4s. 4 plus 4 plus 4 is 12. And equally as clearly, 3 times negative 4 is negative 4 plus negative 4 plus negative 4, which is negative 12. Now, if 3 times negative 4 is negative 12, then negative 4 times 3 must also be negative 12. Now, what does that mean? What does multiplying by a negative mean? If you covered up the negative in negative 4 and said, well, 4 times 3 is 12, and negative 4 times 3 is negative 12, what that appears to mean to me is that multiplying by a negative means multiply without looking at the negative and then change the sign, since the negative means the opposite. So multiplying, for example, negative 8 times negative 5 would mean 8 times negative 5 is negative 40, and then change the sign. It would be positive 40. So multiplying by a negative simply says multiply and change the sign. Now, we could write these rules and memorize them, but to me it's a lot simpler. If I multiply by a positive, just multiply. If I multiply by a negative, cover up the negative in my mind, multiply, and then change the sign. Dividing is really the same as multiplication. It's multiplying by the inverse, if you will, and therefore the rules for dividing are the same. If I divide by a negative, I divide and change the sign. If I divide by a positive, I simply divide. When working with signed numbers, there must be a way to indicate the magnitude, the amount of the number. Because remember, a signed number, or an integer, has a direction, positive or negative, and an amount. And that amount, or that quantity, is called the absolute value. The absolute value is the distance that number is from 0, without regard to direction. So we can see that the absolute value of negative 6 is 6. So is the absolute value of 6, because both negative 6 and 6 are 6 units from 0. And the symbol for absolute value are 2 little vertical line segments in which the number appears. So the absolute value of negative 6 looks like a negative 6 trapped inside these 2 little line segments. And what that means is forget about the negative, talk about the magnitude, the amount of the number. Mathematically, the absolute value of an integer is a whole number. That is, it's 0 or some positive integer. In our common use, our counting numbers, 1, 2, 3, 4, 5, and the positive integers, positive 1, positive 2, etc., are considered the same. Mathematically, they are not the same. Positive 2 and 2 are different mathematically. 2 is a counting number without regard to direction. Positive 2 is a directed number. It has a meaning. So, again, if you're not a mathematician, go ahead and continue to use positive 2 and 2 interchangeably. I certainly do. Finally, we come to rational numbers. A rational number is one that can be written as the ratio between two integers, provided that the second integer is not 0, since we cannot divide by 0. The rational numbers are comprised of integers and the fractional numbers. Integers are rational since, for example, -4 can be written as -4 divided by 1, or -4 over 1. And obviously, fractions can be written in one of three ways: fractions, decimals, percents. The earliest writing of fractions, historically, was limited to the reciprocals of numbers. By putting a symbol over, for example, the number 3, we would have 1/3. That same symbol over 10 would be 1/10. In some cases, fractions that were not simply reciprocals, that is, reciprocals of whole numbers, were written by combining reciprocal fractions. For example, 2/3 is 1/2 plus 1/6, and that's how 2/3 was written. The rules for operating with fractions can be a source of confusion unless one realizes that the rules are really the same as the ones we've used for counting numbers. The key is the place value is the denominator of a fraction. To add or subtract counting numbers, one must align the place value. We add numbers in the tens place to numbers in the tens place. This is true for fractions. Only fractions with the same place value, the same or common denominator, can be added or subtracted. When we multiply counting numbers, we multiply each digit in one number by each digit in the other number. And we multiply those digits, we also multiply the place values. Similarly, when we multiply fractions, we multiply numerators, because those are like the digits, and multiply denominators, those are like the place values. If working with fractions is a problem to you, I would suggest to obtaining the teaching company series Basic Math, because in that series we discuss fractions and their operations at great length. But we really don't have time in this series to spend time on that. Once a place value system came into being, that is the place value system of the Hindus and translated by Arabs and then eventually came to Europe, there was a need and an opportunity to have place values that were fractions. And thus we created the decimal system with hundredths and tenths and thousandths, etc. To add or subtract decimals, we simply line up the decimal points, because the decimal points, or in some countries the decimal commas, indicate where the ones and tenths place are located, and therefore by lining up the decimal points, we line up all the place values. Multiplication and division of decimals are the same as operating with whole numbers. The difference is that we have this decimal place, this decimal point. And again, I refer you to the Basic Math series if you still have problems with decimals, because in that series I explain how decimals are operated with and the reason those methods work. It's not just magic. The simplest form, and the form you find most often in the newspaper to report a fractional number, is the use of percents. And the reason that's so simple is all percents have the same denominator, 100. So 8% means 8 100ths, and 150% means 150 100ths. We generally do not concern ourselves with adding or subtracting percents. If we did, 8% plus 10% is just 18%. There's no magic there. But the percent as a ratio of a number from 1 to 100, we get involved in looking at solving certain types of problems. And basically, all we care about, because remember, a percent is a ratio, is that the percent number divided by 100 or over 100 is equal to the is number over the of number. And the is number, for example, is 8% of 12 is what? 8 is the percent number, 12 is the of number, 8% of 12, and the is number is what we're trying to solve. and therefore we would solve that proportion, percent over 100 equal is over of. Again, I hate to keep mentioning this, but a complete discussion of percents and percent problems can be found in basic math. What I'd like to do now is to look at patterns involving rational numbers. The first pattern we'll investigate concerns converting fractions to decimals. Fractions whose denominators have only powers of 2 and 5 as factors can be converted to terminating decimals. For example, 1/2 equals 0.5, 3/40 equals 0.075, 17/25 equals 0.68, and so on. All other fractions have decimal representations that are repeating. At some point in the decimal representation, there's a cycle of repeating digits. 1/3 is 0.333, and so on forever. 4/11 is 0.363636 forever. 5/6 is a little different. 5/6 is 0.8333. So the 8 starts out, and then we have the 3, and the 3's repeat, but the 8 is never seen again. 5/12 we have 0.41666. The 6's repeat forever. The 4 and 1 only are at the beginning. An interesting pattern can be found when we're dealing with fractions whose denominator is 7. 1/7 is 0.142857 repeated, while 2/7 is 0.285714 repeated. If we look at each of those 6 decimal representations, 1/7 through 6/7, we will notice that the order of the digits is exactly the same, 1, 4, 2, 8, 5, 7. The only difference is which is the first digit. For 1/7, the first digit is 1. For 2/7, it's 2. For 3/7, it's 4. But after that, the order of the digits is the same for each of the 6 representations. Now, there's another interesting fact about the decimal representations of sevenths. If you take the 6-digit cycle, for example, 285714, which is your 2/7 cycle, and split these 6 digits into 2 groups of 3 digits, 285 and 714, and add those 2 numbers up, you get 999. This is true for all of the decimal representations of sevenths. If the fractions that have 13 or 19 in the denominators are written as decimals, the same 2 patterns are observed. The cycle for each decimal that has the same digits in the same order, the only difference being the first digit. This is true for all the fractions with 13ths, and again true for all the fractions with 19ths. If the cycle for a particular decimal is split in half, and all these decimal cycles are have an even number of digits, the sum will always be a group of 9s. So if, for example, you have a decimal that has a cycle of 8 digits, if you add the first 4 digits to the second 4 digits, you'll get 9999. And there are mathematicians who actually investigate this, and there's very good reasons why this happens. But as a young person, I just thought this was intriguing, that somehow, without the benefit of a Congress, in mathematics, these rules were promulgated, and they're always true. Very interesting. Another intriguing pattern has to do with a cycle of 5 fractions. And actually, it's 5 any numbers, but it's interesting with fractions because it gets kind of messy. And every once in a while, we got to do a messy problem to appreciate calculators and computers. We select 2 numbers. In this case, we'll select 2 fractions, 2/5 and 1/3. And that's a sequence. 2/5 comes first, and then 1/3. The rule for this intriguing pattern is take the second number and add 1 to it. So 1 is added to 1/3 to give us 4/3. And then divide that new number by the first number, in this case 2/5. And 4/3 divided by 2/5 happens to be 10/3. We then take this 3-number sequence. We now have 2/5, 1/3, 10/3. And we take the third number, 10/3, add 1, which gives us 13/3, and divide by the number that preceded it, that second number, 1/3. And 13/3 divided by 1/3 is 13. Which, remember, is a rational number because we can write 13 as 13 over 1. Now we have 4-number cycle. 2/5, 1/3, 10/3, and 13. We take that 4th number, add 1, 13 plus 1 is 14, and divide it by the 3rd number, 10/3. 14 divided by 10/3 is 21/5. So we now have the fifth number of a five-number cycle. And now comes the blare of trumpets and the roll of drums, because when we take 21/5 and add 1 to it and divide that by the previous number, 13, we get 2/5. What's so special about 2/5? Well, 2/5 is the first number. We're back to this cycle, and it will go on forever. No matter what two numbers you pick, it will work that way. Now, why does it work? How do I know it works? I did 4 million examples? Of course not. We get to the algebra section of this series, we will prove algebraically that this works for any two numbers. But right now, suffice it to say, 2/5 and 1/3 gives us back to 2/5. Another thing I like to look at is an interesting way of converting a decimal back into a fraction. Now, we said that decimals are either a terminating decimal like 0.27 or a repeating decimal, 0.272727. Well, let's say we had a repeating decimal and we said, okay, what fraction was equal to that repeating decimal? Since we knew a repeating decimal had to be a rational number, we had to be able to write it as the ratio of two integers, what could that possibly be? So let's take 0.376376 forever. Obviously, it has a three-digit cycle of 376. What does this equal? Well, we multiply 376, the repeating decimal, by 1,000. Why 1,000? Because if indeed we symbolize the number we want, this fraction that's really equal to this 0.376376 as n, some unknown fraction, and we multiply it by 1,000, what that does is it multiplies and gets us the first three digits in that cycle to the left of the decimal point. So we now have 376.376376. Now remember, there was an infinite number of 376s. So even though we multiplied by 1,000, there is still an infinite number. So 1,000 times this n is equal to 376.376 forever. We then subtract n. We subtract the number. And of course, 1,000n minus 1n is 999n. We subtract 0.376 repeating from 376.376 repeating, and we get 376. And we now have a very simple equation: 999 times something equals 376. And of course, that means that n, the fraction we wanted, is equal to 376 divided by 999. This fraction cannot be simplified. And this is the same fraction as 0.376 repeating. You say, what's so interesting about that? Well, to me, it says, look, I have a rule that says every fraction that's not a terminating decimal is a repeating decimal. And now I say, wait a second, I have a way to in effect, to prove it backwards, that if I have a repeating decimal, I can get a terminating decimal. So, for example, if I had 0.45252, and I would multiply that by 1,000, and I would have 452.52, and then I would multiply it by 10, which would give me 4.5252. Subtracting 1,000n, the fraction I want, minus 10n would give me 990n, and the 452.5252 minus the 4.5252, again repeating, would give me 448. The decimal portion drops out because they're both infinite repeating decimals. And I wind up with 448 over 990. This can be simplified to 224 495ths. So 0.45255252 repeating is equal to 224 495ths. So we've seen what a rational number is. We've seen that they can be expressed as fractions, decimals, and percents. We've talked very briefly about some of the rules. We've also looked at the creation of zero and the integers. And we've seen some hopefully interesting patterns as to how we use rational numbers. In our next lecture, lecture number 4, we will discuss numbers that are not rational. Perhaps you have an in-law that's not rational, and we might find him or her in this next lecture.